Okay, Ray, welcome to the Health Path podcast. It's nice to speak with you again after what's probably been about 3 years since we last spoke.
Yeah, good to catch up. It's great.
Yeah,
It's been a strange 2 years, but it's good to catch up.
yeah, it is. I think I sometimes look back and I continually get surprised how long it's been since I've spoken to someone or since an event, because the last 2 years have just been a bit of a write-off in some ways. But I'm really looking forward to this conversation. I said to you off air that towards the end of last year, I delivered a webinar on mitochondrial health and leaned on your brilliant book on mitochondria to help with that. And I think it was only really through reading the book and kind of preparing for that webinar that I started to get a bit of an understanding of just how important mitochondria are when we're talking about pretty much any area of human health. Before we dive into what they are, what they do, how we can support them, do you want to just, for those listeners that aren't yet familiar with you, just introduce yourself and give us a bit of a background?
Yeah, so I'm Ray Griffiths. I've got a master's degree in personalized nutrition from CNELM in Wokingham. I do teach at CNM as well. I teach the aging, MS, Parkinson's, and dementia course there. The clients that I mainly see are people with Parkinson's. That's the kind of clientele I see. And mitochondria are incredibly important in that aspect. So one of the big things I do is try to help with their mitochondria. I also at CNELM, I also lecture on cancer and nutrition as well. And again, mitochondria are important. They're important everywhere, but they're really important there. And in cancer, it's more to do with programmed cell death, that mitochondria will tell our cells when to die through something called apoptosis. And so in Parkinson's, mitochondrial dysfunction will lead to poor energy getting to our dopamine producing neurons. But in cancer, it will be mitochondria not telling cells when to die quick enough. So something like neurodegeneration, our cells, neurons are dying too quickly, but in cancer, the cells are not dying at the right time. They're living too long. So but again, mitochondria are involved in both. So yeah, that's been my, that's my training. But my personal journey was really through chronic fatigue. In the mid-90s, I started studying nutrition because I had chronic fatigue. And I wanted to try and understand why. So energy has always been something that I've been fascinated by. And just really fascinating how when I changed my diet and my lifestyle, that my energy levels started to return. I'm still vulnerable. I still noticed drops in energy. So yeah, it's really, really good that it's almost like a survival thing. I wanted to know about my mitochondria to maintain my own health. And from my master's degree, my dissertation was on Parkinson's and mitochondria. And it was really exciting doing that dissertation because all the latest research was about how mitochondria are not just these, they're called organelles. They're like a part of the cell. It's like a mini organ within a cell. And they're called organelles. And they're called organelles because they're not passive. They kind of have this life of their own because they used to be bacteria. They were once bacteria that have been, through evolution, they've joined together with our cells to give us energy. And so over the last 15 years, we've started to understand just they've got this amazing innate intelligence where they're able to engage in quality control. They self-regulate. Frequently they might only last for 3 or 4 days. Say in the liver, they might only last for 3 or 4 days. So they engage in this quality control, and they work to give us our energy. They work as a community. They talk to each other. They talk to our DNA, and I say talk in the loosest possible terms. But to keep our energy going, they're working together, they communicate, and there's some mitochondria will, particularly in our hearts, they have this thing called kissing, where if one mitochondrion, that's a single a singular mitochondria. Mitochondrion is the singular term for it. If one mitochondrion is struggling, another one will go up to it and kiss it and inject nutrients into it to enable that other one to survive. They've also have things called nanotubes as well, where they can have like straws where they inject some nutrients in as well. And in the brain, stem cells have been seen to do this as well. Stem cells have been seen to go around and even inject mitochondria into struggling neurons to help them survive in certain circumstances. So it's fascinating what the body does to maintain its energy and what mitochondria do to maintain community and keep that quality level up. It's absolutely fascinating, and I recommend anyone to read a good book, maybe mine, I don't know, but about these fascinating organelles and how they keep us alive.
Yeah, and as you said there, from like an evolutionary perspective, we are where we are today, not just as humans, but I guess all life on this planet as a result of mitochondria and sunlight. And you talk about in your book, I love something like mitochondria, the harvesters of sunlight.
Yeah.
And I just love that concept.
Yeah, so we don't often think about that, the way what we eat, the food we eat. So through photosynthesis, the plants are harvesting sunlight. They're taking those photons of sunlight energy and they're embedding them into the carbohydrates and fats and proteins, embedding that energy. And then when we eat those foods, whether it's from animals that we eat plants or we eat the plants directly, that harvested sunlight or that trapped sunlight energy is harvested. It's released in slow amounts comparatively. And our mitochondria are busy putting that sunlight energy out and then translating that into energy, ATP or adenosine triphosphate, which is our energy currency to provide the energy to our whole body. And so for many people, they may have heard of the electron transport chain or ETC, and slowly those photons of sunlight are released. There's high energy electrons that carry this sunlight energy, and the electron transport chain slowly releases it to produce ATP. And we need the best to release that sunlight energy. We need good membranes to release it. So we need to be eating good fats, good phospholipids to hold that charge. And as I mentioned to you before we started this recording, that charge across that membrane, it's about between 4 and 6 nanometers wide, that membrane in a mitochondria, and it holds about 150 millivolts. And this is the work of Nick Lane at UCL. He's studied this. And if you work out per meter, so you expand that nanometers up to a meter, that 150 millivolts works at about 30 million volts. So per meter, our mitochondria are producing size for size 30 million volts and more energy than our national grid holds size for size. And we've got not just millions of mitochondria, we've got trillions of mitochondria in our body. So we've got trillions of little bolts of lightning happening every single day for every single day of our lives. And this is huge amounts of energy coursing through our body in our veins. And when we appreciate that, no wonder when we get dysfunction that we'll get tired, we'll get brain fog, we'll get various degenerative conditions if we don't keep our mitochondria working. And I think once we start to appreciate just the power of what these little organelles do, we can get to work and really respect our body.
Yeah, I think it really blew my mind and shifted my perspective on what we want to be thinking about when we're trying to improve our health and well-being. And again, we had a bit of a chat off air where we covered a few things that I'm desperate to make sure that we cover in the recording. But one of them I mentioned was around, I'm not sure if it's in your book or a paper, but the structure of the human body is kind of dependent on where the mitochondria are needed most. So you've mentioned the quantity of mitochondria in sort of dopamine producing neurons, for example, and we have lots of mitochondria in the heart and the liver. So they're kind of, and it makes sense, they're sort of concentrated around the bodily organs and sites where energy is most dependent, I guess.
Yeah. So the dopamine producing neurons has been estimated there could be as many as 2 million mitochondria. When you consider that an average cell is about between 600 and 6,000 mitochondria. There's a quantum leap in the amount of mitochondria needed, and it just shows you just how energy hungry our neurons are. And Parkinson's, for example, what we find with people with Parkinson's is they have a global problem with mitochondrial dysfunction, but it's just the dopamine producing neurons that are so hungry that they start to get apoptosis in their dopamine producing neurons because they're so vulnerable. So most of our cells can cope with drops in ATP and the cell still survives. It's not the case for dopamine producing neurons. Dopamine producing neurons are really sensitive to drops in ATP. But yes, other parts of the body, the liver, mitochondria only live between, some say 3 to 4, but it could be as many as 6 days. It depends which studies you look at, but it's very, very short life or half-life they measure them in the liver, because it's such a toxic environment. It's such an environment that's full of oxidative stress. It's a really tough environment. So for mitochondria to help with detoxification and managing a lot of our chemistry, mitochondria have to be turned over rapidly. And one of the big things in the liver that inhibits mitochondria being engaged in quality control is insulin resistance. And this is a big thing for mitochondria. Insulin resistance, when insulin levels are too high, the ability for mitochondria to self-regulate and go through quality control is undermined. And so we can't allow our mitochondria aren't eaten up through something called mitophagy. We have to digest our mitochondria every few days. With insulin resistance, you can't do that. And what happens with insulin resistance is that mitochondria become, they're not turned over, they become more and more dysfunctional. They produce less and less ATP. And in the worst case scenario, not only they're not producing ATP, but the rest of the cell starts to produce ATP, trying to keep them alive, trying to keep them working. And so they become net consumers of ATP rather than actually producing anything. And that's a disaster, an absolute disaster. So insulin resistance, obesity, type 2 diabetes, all these things are catastrophic for our energy. And then what people, if you're on that treadmill of insulin resistance, is people go, I've got low energy, I have more carbs, I have more simple carbohydrates, which then increases the insulin resistance, which increases mitochondrial dysfunction. So yes, other parts of the body, we were talking about, just say cartilage. To keep our cartilage working, we need mitochondria to be helping to produce the energy to maintain cartilage and bone, and all of our structure needs to have decent mitochondria. Our gut wall needs to have mitochondria. We need to have energy to maintain the integrity of our gut wall. We need energy to maintain the integrity of the blood-brain barrier, the connection between our body, our peripheral circulation, and our brain. Our brain likes to be independent. It has its own environment. It cuts itself off from the rest of the body, and it likes to choose what it allows in and what it pushes out. That's really important. And if the blood-brain barrier becomes leaky through lack of energy, for example, or too much inflammation, then there's toxins and there's immune complexes that get into the brain that shouldn't get in there. And without sufficient mitochondria, we can't maintain that integrity. Interestingly, one of the things that does seem to undermine the integrity of mitochondria in the blood-brain barrier is aluminium. Aluminium, and Dr. Chris Exley is, or Professor Chris Exley now, I think his name is, he's done a lot of work on this, how aluminium can preferentially antagonize things like magnesium, which is needed for mitochondrial function, and that can undermine the blood-brain barrier too. And bearing in mind we use aluminium all over the place, we're a bit too gung-ho with it, considering how dangerous it is to the body. Luckily, we don't absorb aluminium that easily, but it's when it's injected, say as an adjuvant, that's the real concern.
Okay. I mean, it's fascinating, especially the sort of the barrier element. So obviously a lot of our listeners and certainly our sort of community and customers are struggling with digestive issues. And you've mentioned there that mitochondrial function is important to maintain a healthy gut lining. And I think I'm right in saying they're also important from a immune cell perspective at the gut lining. So I think I've read a paper talking about how the mitochondria are almost kind of regulating the activity of immune cells. And when they get exposed to a pathogen, there's sort of a shift that allows these immune cells to kind of upregulate and become sort of busier.
Yes.
And also there's research connecting it with just microbiome diversity, I think, as well.
The bit that I'm interested in, I'm not sure about diversity, but there's a shift in the way the mitochondrial phenotype. So the type of, also mitochondria change their behavior to allow a change in phenotype in immune cells. So when our immune cells move to more inflammatory, when we get effector T cells, they tend to shift their metabolism more towards anaerobic respiration. So when there's anaerobic respiration, we think, well, mitochondria are switched off. That's not exactly the case. What happens is when we have more inflammation, our immune cells shift towards anaerobic respiration using glycolysis without oxygen. And mitochondria stop making so much ATP and rely on glycolysis in these effector T cells. And mitochondria start making help support the manufacture of components of cell walls. So they become little, I call them like builder's merchants. They turn from being a power station to a builder's merchant, that the mitochondria, rather than using citric acid for energy, they export the citric acid, which then becomes acetyl-CoA. It becomes a building block for saturated fats and cholesterol, which then so when we have an immune response, we have to multiply our immune cells rapidly. There's a massive expansion of these immune cells, and mitochondria are behind many of the components that are needed for this rapid expansion. So these effector T cells change their metabolism to allow mitochondria to be a manufacturer rather than making ATP. And this is great when it's working well, when we need inflammation to fight infection. But when it becomes a chronic inflammatory condition, it's the last thing we want. We don't want these mitochondria making all these inflammatory components. We want mitochondria to be giving us energy. And again, things like inflammation, chronic inflammation, insulin resistance will be shifting the phenotype of our immune system towards an inflammatory phenotype, which is not what we want. So trying to feed our mitochondria in a way that keeps them making ATP and making less of these inflammatory components. There's a term called de novo lipogenesis. Have you heard of that term?
I've heard of it, but I couldn't tell you what it is.
It happens in cancer, it happens in chronic inflammation. And mitochondria, so de novo, it's from new. Okay. So it's not the fat coming in to us from our diet. We're making, so lipogenesis, it's the manufacturer, it's the creation, lipofat. So brand new fats created internally. And the irony here is that eating lots of simple carbohydrates will create lots of these internal fats. So people avoiding fat and eating lots of carbs are actually just creating more fat. Right. And that's something that people don't realize. But in cancer and inflammation, this de novo lipogenesis relies on mitochondria and an inflamed state, insulin resistance, to be exporting citric acid. That then converts to acetyl-CoA. That then creates cholesterol and fatty acids. That provides cell membranes for inflammatory immune cells to allow these to rapidly, because they're going to need lots of cell membranes, and it's going to be created from these components from mitochondria. All the components within the Krebs cycle or the tricarboxylic acid cycle, all these organic acids can be repurposed and can be the building blocks for making proteins and nucleotides and nucleosides. So mitochondria are not just making ATP, they're these manufacturers of many parts of our body too. And that's a real fascinating insight that I've slowly over time started to appreciate.
Yeah. I think that's, if I'm sort of, my perception of the research over the last 15 years or so is, as you say there, we've gone from thinking that, and they're still often referred to as the powerhouses or the energy factories of the cell, but There's a quote I remember in the research talking about how they kind of sense, integrate, and respond to the environment. So they're more than just energy producers. They're orchestrating numerous processes within the cell and therefore the body. And I guess that's why they're just connected with most conditions that we're all familiar with that seem just to be increasing in frequency in the modern world.
Yes, yeah, there is an innate intelligence. There's obviously not a brain, but because they're organelles, they've been given a term which kind of gives you the idea that they're more than just this passive object. They're an organelle. They have an innate intelligence. And what I found fascinating is there's a researcher called John Lemasters who really tapped into this innate intelligence of mitochondria. And he was the one that looked into mitochondrial dynamics and just how they work as a community, how they get digested and repurposed. And there was a real reluctance to accept from mainstream academics that they were quite intelligent. And I've seen this going through research. There's always this pushback from the mainstream academics about any innate intelligence within a living system. And why would they eat themselves? What's the point of that? And then when you start to understand, it's through quality control that the mitochondria are continually undergoing improvements in quality to maintain a pool of mitochondria that are really healthy, to keep our heart going, to keep our central nervous system going, to keep our gut going, our legs, every part of our body, our muscles. We need to have this pool of really efficient mitochondria. And we saw this, I mentioned about apoptosis, programmed cell death, that mitochondria are involved in as well, that I think it's Kerr et al. About 1972, they discovered apoptosis that mitochondria are involved in. And this is programmed cell death. And again, at that time, there was a real pushback. Like, why would cells choose to die? Obviously, we want eternal life. But so academics didn't get it, that the body would actually choose to end the life of a cell to maintain the life of the whole. It's a continual obstacle that we're coming across with academics. There's always this pushback to try and keep the body stupid, I suppose. And I think people working in the naturopathic and holistic fields really respect this innate intelligence within a living system, and mitochondria are part of that. They've got amazing innate intelligence. And so for us, there's a shift, rather than just taking over and taking control of a stupid body, which is what I think allopathic medicine does. It's just a dumb body. We have to give it the right chemicals and move on. We're a little bit different. We're trying to immerse ourselves in the intelligence of this body, in the intelligence of mitochondria, and then working out how we can help it try to do what it's trying to achieve. And so there's a whole narrative in our mind of what it's trying to achieve, what it's not achieving, and how we can help. I hate using the word nudge because that's been used too much just recently, but you're just hoping to nudge it in the direction and support it and give it what it needs to allow it to function in the way it wants to function, not take control. And that's the big difference. That's the subtle difference.
Brilliant. Okay. So, as I guess a little quick summary, we kind of mentioned what they are and a tiny bit of the evolutionary history of this, of how a bacteria and archaea merged hundreds and hundreds of thousands of years ago.
Yeah, 1.5 billion years ago. Yeah.
Okay, there we go. And that's kind of led to life on this planet. Also, I guess, as a result of us being at the right distance from our sun, thinking about Professor Brian Cox's documentary that he did recently around sort of the universe, which he picked up on a lot of what you were mentioning earlier on around sort of photosynthesis and how the mitochondria and sunshine are kind of just the prerequisites for life of all species on this planet. We've mentioned some of what they do. Obviously, we could talk for days really about that side of things. And you've mentioned so far a few things that are both good and bad, so to speak, for the mitochondria. So things like healthy fats and phospholipids, aluminium potentially being really problematic, insulin resistance, obesity, diabetes. What else do we know is both beneficial or potentially problematic when we're thinking of mitochondria health, function, and quality control?
Yeah, there's something called hormesis, which is really important for mitochondria too. People might not have heard of it, but hormesis, sorry, I've got a little frog in my throat, sorry. So we need a little toxicity in our lives. And the biggest toxin that we most appreciate is exercise. That's the biggest toxin in our lives, in a way, for most of us. That when we exercise, we create free radicals. And these free radicals have to be dealt with. So the body's evolved to deal with these free radicals, that the body senses these free radicals being created by exercise. And there's something called NRF2, it's a transcription factor, which picks up on the free radicals generated by exercise. It goes to our DNA, and there's something called the antioxidant response element. And the antioxidant response element starts making lots of antioxidants like glutathione, catalase, superoxide dismutase. And it makes one particularly important one. Well, it makes superoxide dismutase for mitochondria, but there's another one called NQO1 as well, which is really important for mitochondria. So when we exercise, we create free radicals, but in doing so, we end up, the net effect is through hormesis. It's this mild toxicity creates a much greater beneficial effect. So as long as we're healthy, we can respond to exercise by making lots of antioxidants and actually have a net effect of being more healthy. Same goes for fruits and vegetables too. That within our fruits and vegetables, many of the polyphenols in our fruits and vegetables, particularly cruciferous vegetables, for example, these polyphenols are mildly toxic. They're plants' own sort of pesticides in a way, and they're mildly toxic. We know they do have antioxidant effects, but they're very small amounts of antioxidant effects. The biggest effect is this mild toxicity. And again, the mild toxicity is picked up upon by NRF2. It tells our DNA to respond to these polyphenols, these plant compounds. It responds to them. It makes more glutathione, superoxide dismutase, etc. And so the polyphenols will then upregulate our antioxidants and support mitochondria. So that's a really fascinating, again, it relies on understanding the innate intelligence of a living system, how a living system has come across these toxicities through exercise, through plants, through being involved, like it being in a sauna, through heat, through sweating, through exercise, or through cold extremes. All these things are challenges to the body, and the body's evolved to deal with these challenges, to not only overcome them, but to evolve and actually benefit from them. And I love that kind of intelligence. But also mitochondria generate reactive oxygen species themselves. And this is an important, so not too many dysfunctional mitochondria produce too many reactive oxygen species. But when mitochondria are working hard, they produce reactive oxygen species. And these reactive oxygen species again go to DNA. And the DNA goes, oh, okay, mitochondria are working hard. They need some help. They're telling me they need help. So then DNA will send nutrients to mitochondria. They'll express more antioxidants and then support mitochondria. And that's called mitohormesis, M-I-T-O, mitohormesis. So that there has to be a continual dialogue between mitochondria and DNA. And in Parkinson's, we know that doesn't happen very well. So people in Parkinson's, their mitochondria can't communicate as well as it should do with our DNA. And we think that one of the reasons may be that people with Parkinson's frequently have polymorphisms or genetic difficulties with producing folic acid, that folate is essential in that communication between our DNA and mitochondria, and people with Parkinson's frequently have problems with that.
Interesting. Okay. And actually that brings up, I'm not sure if you'll have this at the sort of on the tip of your tongue, Ray, but it brings up that sort of conversation around why do we have mitochondrial DNA in the first place? Why do they not merge fully? Because I believe there's still a little bit of mitochondrial DNA there, and we understand there are some specific reasons for that, I think.
Well, yeah. So as we mentioned a few moments ago, mitochondria used to be bacteria. They're alpha proteobacteria, and they joined together with another organism called archaea. So they both had their own DNA, and the discovery that mitochondria were actually once bacteria was because of that DNA component. We realized that was the case. Lynn McGullis was really pushing hard in the 60s to say mitochondria used to be bacteria, and she's like, stupid woman, we're not going to listen to her. How could they be bacteria? That's really silly. But she kept pushing along, and eventually, with her, it wasn't originally her theory, but she reinvented it and made it her own. But when mitochondrial DNA were discovered, they then realized that she was right all the way along. And I love her for that. She was just like, no, these men, I'm not going to listen to them. I'm right. And she was so doggedly determined. So yes, it's brilliant. But yes, mitochondria have their own DNA because they used to be bacteria. But as time's gone on through evolution, there's been, again, this dialogue between mitochondria and DNA, and there's more and more mitochondrial genes that were gradually shifted to DNA. So the DNA that exists in mitochondria tend to be just the really important ones for the electron transport chain and a few other proteins. It keeps them lean and keen. It means they're not overly complex. They've got their own DNA, but they do need nuclear DNA to keep them functioning. They need nuclear, and so they need this continual dialogue. But the flip side of it is that in inflammation, we can use mitochondria because they used to be bacteria. We can use the mitochondrial DNA and components of mitochondria to stimulate an immune reaction. And that's essential in small amounts, but in large amounts, it leads to chronic inflammation and degenerative disease. So when mitochondria start to break down, they're no longer our helpful allies. They're seen as what they always were, which is bacteria. So the components, when they leave mitochondria, the cell goes, this isn't us, this is something different. This is bacterial components. So mitochondrial DNA is seen as if it's bacterial DNA, and then the immune system kicks in. Sometimes the immune system does this on purpose. It sacrifices mitochondria. I think neutrophils do this. Neutrophils will create a net of mitochondria to drive up inflammation. It's called a mitochondrial net, I believe. And they will sacrifice these poor mitochondria to drive an inflammatory response. So mitochondrial DNA is great in mitochondria when it's working, but it can be something called a DAMP, a damage-associated molecular pattern, which will drive up inflammation. And if someone's got chronic inflammation and their cells are breaking down, then these mitochondrial components can be, in a negative way, driving that inflammation as well. We know in depression, people with depression have higher levels of mitochondrial fragments in their central nervous system. That the excessive stresses that are going on in that person's life can lead to excessive inflammation in their brain and causing mitochondrial dysfunction, and the mitochondrial components are driving inflammation too.
Fascinating. Yeah, I was going to sort of mention the whole DAMP element for the practitioners listening today. And is that we've got sort of, my understanding is receptors on certain immune cells which are kind of able to sort of receive or detect these damage associated molecular patterns that then
We've got toll-like receptors. We've got toll-like receptors that can can receive these. And toll-like receptors on the immune cells, it sounds complicated, but I don't know whether anyone knows, but toll, it's not toll as in a toll gate, it's toll, it's the German researchers that found these receptors. When they found the receptors, I think it's on Drosophila flies, I think they found them. They were so excited that they found these immune system receptors that they shouted excellent in German, and excellent in German is toll. So they're just excellent receptors. They're nothing. So I love breaking things down, because academics tend to have this habit of making things seem more complex than they are. So I like to have a little laugh with myself so I can make sense of stuff. But yeah, these toll-like receptors that pick up these so there's bacteria and pathogens will have they will produce things called PAMPs, or pathogen-associated molecular patterns. Our own breakdown products from our cells, from our mitochondria, can have similar effects to these pathogen components, and they're called DAMPs, damage-associated molecular patterns. Some people even calling them PAMPs, MAMPs now. They call them microbial-associated molecular patterns. So it's all part of the innate immune system that is on the front line. It can recognize these either pathogen components or our own cellular components and put the innate immune system into action, which in usually it's a good thing, but in chronic inflammation it can be something quite negative. And there's one hypothesis about chronic fatigue, is that it may be, there's one hypothesis where there's a shift from PAMPs to DAMPs, that someone with an infection that becomes chronic, their immune system is not able, their immune system suppressed, it's not able to fight the infection, that it becomes chronic, and the damage from the PAMPs starts causing damage to our own cells. And so there's this shift from the pathogen molecular patterns to our own damage associated molecular patterns, and it ends in this cycle of degeneration and breakdown. And so some people suggest that it could be chronic fatigue is this shift between the pathogen breakdown products to our own damaged cellular byproducts.
And is that what some people refer to as kind of sterile inflammation, where kind of there's no longer an actual organism like a bacteria or a virus, but it's that chronic response to our own bodily tissues or cellular components?
Yeah, that's a really good point there, because it reminds me, yes, it's sterile, but also there's a psychological aspect too. There's a stress and psychological aspect to sterile inflammation. And it's Dr. Kevin Tracy really found that out. Dr. Kevin Tracy, he had an infant that was scalded, and it died of sepsis in his arms. And he thought it was going to survive because it had no bacterial, it was on antibiotics. There was nothing that because he thought that sepsis was something to do with, say, a bacterial component that was driving inflammation. But no, the nervous system has the ability to suppress inflammation too. And so things like just psychological connection with people, seeing people's faces, touching people, being cared for will produce oxytocin, and will have an effect on the vagus nerve. And the vagus nerve, when we're connected to people, when we love people, when we care about people, when we feel connected, we will produce the oxytocin, which will calm down inflammation. So there's an increased risk of chronic inflammation, and it's sterile because it's more of a psychological connection. And again, mitochondria. So the oxytocin will be upregulating acetylcholine or acetylcholine in our central nervous system. It will be down-regulating toll-like receptors. It will be supporting mitochondria, that mitochondria have receptors for acetylcholine, and it will calm down inflammation and upregulate ATP. It will reduce inflammation in our brain. So that human connection, which we've been really struggling with in the last 2 years, by socially distancing, not connecting with people we care about, people in care homes and things like that, not seeing their loved ones, it will drive up inflammation, it will reduce their mitochondrial function, it will inflame their brain. And so if someone's got dementia in a care home and they're not seeing the ones they love, that's catastrophic for their mitochondria in their brain.
Absolutely. And on that note, have you done any reading around the role that sort of photobiomodulation or light therapy plays within mitochondria?
I haven't done that much. I do know that someone who's good on that is Gillian Crowther.
Okay.
So you might want to get her on.
Yeah.
And get Gillian Crowther on. She last year gave a presentation to Bristol Bant. Sarah Myhill and Gillian Crowther were on that, and she did a really good presentation on that light modulation. But we do know that, yeah, mitochondria do seem to be sensitive to light, and do generate a certain amount of ATP. So that the chloroplasts that are in plants, so plants have mitochondria and have chloroplasts, which are like cousins of mitochondria. And so by eating green leafy vegetables, we're eating the chloroplasts. Chloroplasts have lots of antioxidants in them. I think there's things called plastoquinones, which are in chloroplasts, which can act as mimics of CoQ10. So the plastoquinone is a quinone. It works like CoQ10. So by eating green leafy vegetables and eating the quinones within those green leafy vegetables, that can support CoQ10 and the mitochondria. As for vitamin K, vitamin K is either phyloquinone or minoquinone, which is K2. It's a quinone, it supports CoQ10. So CoQ10 is very difficult to absorb, saying that only 1% gets across our gut wall when we consume it as a food or as a capsule, but vitamin K and the plastoquinones are far more absorbable. So yeah, these chloroplasts are like our cousins, and mitochondria in a similar way to these chloroplasts can engage in some degree of photosynthesis, according to some researchers. Some people poo-poo that, but I think it, from what Gillian's been talking about, it does seem possible.
Interesting. Yeah, I'll have to reach out to her and get her on. I'm super interested in that side of things at the moment. Okay, so I guess finally, we can already speculate about some of the things, I guess, that we could consider from a testing perspective. I understand it's not the easiest thing to kind of look at from a testing perspective, but we've mentioned certain key nutrients that I imagine understanding our status of will help us understand whether we've got sufficient building blocks, whether it's CoQ10, B vitamins, fatty acids to support the mitochondria. Is there anything else that we can consider from kind of a testing perspective to get insight into this?
Yeah, so when I'm working with Parkinson's, if someone can afford it, I will use organic acid tests, and Genova's NutriVal is one that I really like because that has vitamin D. The vitamin D is really important for mitochondria too. Alpha lipoic acid, that's incredibly important for mitochondria. Not only does alpha lipoic acid help with the shift from glycolysis to going to oxidative phosphorylation in the electron transport chain, etc. So alpha lipoic acid is a really important bridge. It also helps with insulin sensitivity, which will help with mitochondria too. All the B vitamin status, to be able to make the NADH, FADH, etc., we need to have the correct B vitamins. Great Plains, that their organic acid test does focus more on specific mitochondrial components, but the Genova one has a more overall view. So in a way, I'd almost like both of them, but yeah, you run out of money if you're not careful. I believe Acumed do a mitochondrial test, but I'm not a doctor, so I'm not able to use those tests. Yeah, fatty acids, again, the electron transport chain, the membrane in that electron transport chain needs to have good phospholipids, good fatty acids. So DHA is particularly important in that membrane, I use to support the electron transport chain. I use cardiolipin. I use CDP choline or citicholine, which supports cardiolipin. It's the phospholipid that's in the inner mitochondrial membrane. So I use that phospholipid. I use citicholine. I use the one by Jarrow. So I might, again with Parkinson's, but other people might, if they've got mitochondrial dysfunction, it might be useful to have a toxicity test as well. So I use a Great Plains organic toxic compounds test that Biolab do that one. And frequently you find very high levels of organophosphates, petrochemicals in these people. Really fascinating that I've got two people with Parkinson's, two clients with Parkinson's that have worked in boatyards. They've worked in boatyards for a period of time where they've used anti-fouling products to clear all the barnacles, etc., off the boats, which are really heavy in organophosphates. But they, even after 30 years, they still got these organophosphates in their system, which means it's going to be in their brain. And organophosphates are going to be really difficult. They're going to undermine mitochondria in these people's brains. I mean, many of the organophosphates are designed to cause mitochondrial dysfunction in these organisms. It kills them in that way, particularly I think it's rotenone is one of them, which is actually a natural pesticide. So you think about it, you're using these compounds to undermine mitochondrial function in these. So if you do a test that's got like this Great Plains a toxic profile, and it shows all these levels of toxic compounds, then they're going to be causing mitochondrial dysfunction. There's no doubt about it. If you've got heavy metals, if you've got high levels of aluminium, then that's going to be causing mitochondrial dysfunction. That through the work of Dr. Chris Exley, he's found that the high levels of aluminium will be causing mitochondrial dysfunction. So although you might not get direct mitochondrial tests, which give you direct functional or dysfunctional results, you can kind of triangulate, say, well, you've got this, so that's going to be mitochondrial dysfunction. You've got those heavy metals, you've got those petrochemicals or those pesticides, or the organic acid test is going to be low in that particular component, so that's going to be causing problems. And the fatty acids, that low levels of omega-3s or phospholipids, etc., so that you can start to work out through those patterns that person is going to be struggling.
Yeah, and it's just something that popped into my mind when you were saying all of that is now that we all understand that they are remnants of bacteria, antibiotics can also potentially be problematic.
Yes,
kind of thing.
Yes,
so
absolutely.
Yeah,
antibiotics can be a problem.
Okay, brilliant.
I can't remember his name. There's a researcher who's very into that connection between antibiotics and mitochondrial function, but I've forgotten his name now. But if someone wants to check it out, there's some really good papers on it.
Okay, fantastic. I'm mindful of your time, Ray. So is there anything that you would like to kind of conclude with? Anything that we haven't yet mentioned or that you want to sort of emphasize?
No, I mean, just to really overview, I mean, in the second part of my book, I go through several different health conditions and just focus on how mitochondria are involved in every single one of them. Yeah, so I mean, that's what I tend to do if I'm working with someone. If it's not, say, Parkinson's, I'm working on a different condition. My usual starting point is, what are the mitochondria doing in this? Because so, like, for example, with cardiovascular disease, we know that with cardiovascular disease that sometimes if people have got low HDL, that to get cholesterol out of our cells, we need to have ATP from mitochondria to pump the cholesterol out to get it onto HDL. So some researchers are saying, oh, it seems to be a sign of mitochondrial dysfunction that many people with low HDL just haven't got the energy to pump the cholesterol out of their cells. to put it onto HDL. So it really adds another layer of what you're working with. If you look, say, okay, what are mitochondria doing? What are the studies for mitochondria in this disease? And it adds a wonderful nuanced layer to what you're looking at, and it can open up some new ideas. So I suggest that. And I know I'm biased. I know I'm completely obsessed, but that's what I suggest doing, is just it really opens up some new ideas.
Yeah. Well, I'll put a link to your book into the bio of today's episode, and having read it, I can highly recommend that. It's well worth a read, because it's a pretty big book for starters. There's a lot of content in there, but it's also very practical, as you say. The second half, going through specific conditions, is just incredibly helpful for us to understand that context. So, Ray, thank you so much for coming on. It's been great to chat through this incredibly important organelle, the mitochondria, and I look forward to sharing this with everyone very soon.
Okay, thank you.